Welcome to this lecture on one of the most fascinating puzzles in the history of chemistry. Reactions that ran impossibly fast, and how solving this mystery gave birth to modern surface science and the concept of active sites. In the early 1900s, chemists began noticing something extraordinary. Certain reactions that should have taken hours were completing in mere seconds when a metal surface was present. We're talking about reactions running 1,000 times faster than any theory could explain. Let me set the stage. By 1830, chemists knew about catalysis, but they had no mechanistic understanding whatsoever. Berzelius observed that platinum could facilitate reactions without being consumed. But the mechanism was a complete black box. It was essentially magic. Now here's where it gets interesting. A rate law is not just a mathematical expression. It's a stress test for your proposed mechanism. If your mechanism predicts one rate law and you observe another, your mechanism is wrong. Period. The rate law tells us how the reaction rate depends on concentrations. The exponents m and n must come from the mechanism, not from the stoichiometry of the overall reaction. Let's examine our first case study. The reaction of hydrogen gas with oxygen gas to form water, catalyzed by platinum surface. 2H2 plus O2 gives 2H2O. This is the overall stoichiometry. Let me pose a question. If this reaction proceeded by simple collision theory in the gas phase, what rate law would you expect? You might predict rate equals K times H2 squared times O2, based on the stoichiometry. A third-order reaction. But that's not what researchers observed when platinum was present. The actual rate law was rate equals K times H2 to the first power times O2 to the 1/2 power. Notice that fractional exponent on oxygen. This fractional order was absolutely baffling. How can you have half a molecule participating in a reaction? This is where the concept of surface adsorption comes in. The key insight was that oxygen molecules don't react as O2. They first dissociate on the platinum surface into individual oxygen atoms. O2 plus 2 surface sites forms 2O-S, where S represents a surface site. This is a reversible equilibrium step. Because this is an equilibrium, we can write an equilibrium constant K. K equals the concentration of OS squared divided by the concentration of O2 times the concentration of surface sites squared. Solving for the concentration of adsorbed oxygen, we get OS equals K to the 1/2 times O2 to the 1/2 times S. And there's your fractional order exponent. The square root of oxygen concentration appears because the adsorption equilibrium involves the square of the surface species. The oxygen molecules break apart on the surface, and these individual oxygen atoms are what actually react with hydrogen. The next step in the mechanism is the rate-determining step. Hydrogen gas reacts with an adsorbed oxygen atom to form water and regenerate the surface site. The rate of this step is KRDS times the concentration of H2 times the concentration of OS. Substituting our expression for OS, we get rate equals KRDS times H2 times K to the 1/2 times O2 to the 1/2 times S. If we lump the constants together, we get rate equals K observed times H2 times O2 to the 1/2. This matches the experimental observation perfectly. Let's do a back-of-the-envelope calculation to understand surface coverage. How many atoms can fit on a platinum surface? Platinum atoms in the surface are spaced about 2.8 angstroms apart. The number of sites per square centimeter is roughly 1 divided by 2.8 times 10 to the negative 8 squared. This gives us about 1.3 times 10 to the 15 sites per square centimeter. Now here's a question. If we have 1 gram of platinum powder with a surface area of 10 square meters, how many molecules can adsorb in a complete monolayer? 10 square meters equals 10 to the 5 square centimeters. Number of molecules equals 10 to the 5 times 1.3 times 10 to the 15, which is about 10 to the 20 molecules. Converting to moles, that's 10 to the 20 divided by Avogadro's number, approximately 10 to the negative 4 moles. This is a remarkably tiny amount of adsorbed material, yet it completely controls the reaction rate. This shows you how powerful surface effects can be. Let's move to our second case study, the Haber-Bosch synthesis of ammonia. This is one of the most important industrial processes ever developed. Nitrogen plus 3 hydrogen gives 2 ammonia. On iron catalyst surfaces, this reaction exhibits very interesting kinetics that took decades to fully understand. The observed rate law for this reaction was completely bizarre and unexpected. Rate equals K times N2 times H2 to the 3/2 power divided by the concentration of ammonia. Notice something remarkable. The product ammonia appears in the denominator. This is called product inhibition. The product slows down its own formation. Let me ask you, why would ammonia, the product, slow down the reaction? Think about what must be happening on the surface. The answer is competitive adsorption. Ammonia molecules adsorb onto the same iron surface sites that nitrogen needs to dissociate. The more ammonia present, the fewer sites available for nitrogen. This observation led Irving Langmuir to develop his famous adsorption isotherm in 1916, which mathematically describes surface coverage. Theta, the fraction of surface covered, equals Kp divided by 1 plus Kp, where P is the partial pressure and K is the adsorption equilibrium constant. At low pressure, when Kp is much less than 1, theta is approximately equal to Kp, so coverage is proportional to pressure. At high pressure, when Kp is much greater than 1, theta approaches 1. The surface becomes saturated. Here's what the Langmuir isotherm looks like. At low pressure it's linear, then it curves and saturates at high pressure. The red dashed line shows the saturation limit where every surface site is occupied. When multiple species compete for surface sites, we need to modify the Langmuir model. For species A competing with species B, theta A equals Kapa divided by 1 plus Kapa plus Kbpb. Now let's apply this framework to understand the ammonia synthesis rate law. Step 1 is nitrogen dissociation on the iron surface. This is the rate determining step. N2 plus 2 surface sites gives 2N-S. The rate depends on the concentration of available sites squared, because we need 2 adjacent sites for nitrogen to dissociate. Rate equals K times N2 times S squared. But the concentration of free sites depends on what else is adsorbed. Both hydrogen and ammonia can block sites. The concentration of free sites is proportional to 1 divided by 1 plus Kh times H2 to the 1/2 plus K ammonia times ammonia concentration. Notice hydrogen is to the 1/2 power because hydrogen also dissociates on the surface, just like oxygen did in our first example. When you work through all the algebra, assuming ammonia adsorbs much more strongly than hydrogen, you get rate proportional to N2 times H2 to the 3/2 divided by ammonia squared. This derivation matches the experimental rate law when ammonia is the dominant adsorbed species, which is typically the case under industrial conditions. These puzzling rate laws led to a profound realization: not all surface atoms are created equal. Only certain special sites on the surface, called active sites, are responsible for catalysis. These might be defects, steps, kinks, or specific crystal faces. Here's a critical question. How can we experimentally identify which sites are the active ones? Method 1 is selective poisoning. Add molecules that preferentially bind to certain site types and see how the rate changes. If adding a poison that binds to step edges kills the reaction but a poison that binds to terraces doesn't, you know the active sites are at step edges. Method 2 is structure sensitivity studies. Change the particle size and measure how the rate per surface atom changes. Small particles have a higher fraction of edge and corner sites compared to terrace sites. The small particles have many more corner and edge atoms, shown in red, compared to the large particle. If the rate per surface atom increases as particle size decreases, that tells you the reaction is structure sensitive and edges or corners are the active sites. This active site concept extends beautifully to biological catalysts. Enzymes. An enzyme is a huge protein molecule, maybe 10,000 atoms, but only a tiny pocket of perhaps 10 to 20 atoms actually does the chemistry. That's the active site. Enzymes can be incredibly selective, accelerating one specific reaction by a factor of 10 to the 14 while ignoring very similar reactions. Rate enhancement can be 10 to the 14th or even higher. That's 14 orders of magnitude. Let's do another back-of-the-envelope calculation. How fast can an enzyme work? The turnover number kcat equals Vmax divided by total enzyme concentration. Typical values of kcat range from 10 to the 3 to 10 to the 7 per second. The enzyme catalase, which destroys hydrogen peroxide, has a kcat of about 10 million per second. Each enzyme molecule processes 10 million substrate molecules every single second. This raises an interesting question. What's the absolute speed limit set by how fast molecules can diffuse together? The diffusion limited rate constant is about 10 to the 9 to 10 to the 10 per molar per second in aqueous solution. Remarkably, some enzymes like triose-phosphate isomerase actually operate at the diffusion limit. They catalyze the reaction so efficiently that every collision leads to product. They can't possibly go any faster. Let me introduce you to one of the most important concepts in catalysis, the Sabatier principle. The Sabatier principle states that the optimal catalyst binds reactants not too weakly and not too strongly, but just right. Here's a plot of catalytic activity versus binding energy. The activity follows a volcano shape. The optimum is at the peak. Too weak binding on the left means reactants don't stick. Too strong binding on the right means products can't leave. This explains why platinum is such a good catalyst for many reactions. It binds molecules strongly enough to activate them but not so strongly that products get stuck. Modern surface science has developed incredibly powerful techniques to probe active sites at the atomic level. Scanning tunneling microscopy allows us to literally see individual atoms on a surface. An atomically sharp tip scans across the surface, and quantum tunneling current reveals the position of every atom. Temperature-programmed desorption lets us measure how strongly different molecules bind to different sites. X-ray photoelectron spectroscopy identifies what chemical species are present on the surface and their oxidation states. Let me show you how all these pieces fit together to solve mechanism puzzles. Step 1. Measure the rate law very carefully as a function of all reactant and product concentrations. Step 2. Propose a sequence of elementary steps including adsorption, surface reaction, and desorption. Step 3. Identify which step is rate determining, usually the one with highest activation energy. Step 4. Use pre-equilibrium approximation for fast steps and derive the predicted rate law from your mechanism. Step 5. Compare your predicted rate law with experiment. If they match, you're on the right track. If not, go back and revise. Let me show you a real example: carbon monoxide oxidation on platinum. 2CO plus O2 gives 2CO2. This seemingly simple reaction shows remarkably complex behavior including oscillations and pattern formation. The rate law is K times CO times O2 divided by 1 plus KCO times CO quantity squared. Notice something remarkable. At high CO concentration, the rate actually decreases. The reaction essentially shuts down. This is called CO poisoning. Carbon monoxide binds so strongly to platinum that it blocks all the sites needed for oxygen dissociation. At high CO pressure, the surface becomes completely covered with CO molecules, leaving no room for oxygen to adsorb and dissociate. Here's a practical question. If your catalytic converter is poisoned by CO, how do you regenerate it? The answer is increased temperature. At higher temperature, the CO desorbs more rapidly, freeing up sites for oxygen. The adsorption equilibrium constant equals A times e to the negative delta H adsorption divided by RT. As temperature increases, the equilibrium constant for adsorption decreases, meaning weaker effective binding. Let me tell you about a famous historical debate. Do reactions occur between adsorbed species, or between an adsorbed species and a gas phase molecule? The Langmuir-Hinshelwood mechanism says both reactants must adsorb first, then they react on the surface. A-S plus B-S gives C-S plus S. The Eley-Rideal mechanism says one species is adsorbed but the other reacts directly from the gas phase without adsorbing. A-S plus B gas gives C-S. For most heterogeneous catalytic reactions, the Langmuir-Hinshelwood mechanism dominates. Both species need to be activated by adsorption. However, Eley Rideal can occur for extremely reactive species like atomic hydrogen or certain radicals that react before they have time to equilibrate with the surface. Let me briefly mention the modern frontier, computational catalysis using density functional theory. Density functional theory can calculate binding energies of molecules on surfaces with remarkable accuracy, often within a few kilojoules per mole. The adsorption energy equals the total energy of surface plus molecule minus the energy of the bare surface minus the energy of the free molecule. We can now map out entire reaction pathways on surfaces, finding transition states and calculating activation barriers computationally. This computational approach now guides experimental catalyst design. We can predict which metals or alloys should work best before spending years in the lab. Let's look at a crucial real-world application, the three-way catalytic converter in your car. It oxidizes carbon monoxide to carbon dioxide. It oxidizes unburned hydrocarbons to carbon dioxide and water. And it reduces nitrogen monoxide back to nitrogen gas. The challenge is doing oxidation and reduction simultaneously. You need enough oxygen to oxidize CO but not so much that you can't reduce nitrogen oxides. The converter uses a ceramic honeycomb coated with platinum, palladium, and rhodium nanoparticles. This provides enormous surface area in a compact volume. Modern three-way catalysts remove over 99% of CO, hydrocarbons, and nitrogen oxides when operating at the right temperature and air-fuel ratio. Let me emphasize the broader point. Rate laws are diagnostic tools. They're like medical tests that reveal the hidden mechanism. Fractional reaction orders reveal pre-equilibrium steps, especially adsorption equilibria. Product inhibition reveals competitive binding for active sites. Unusual temperature dependence can reveal mechanism changes or changes in the rate determining step. Let me give you a mind-bending example. Can a reaction have a negative activation energy, where it goes slower as temperature increases? The answer is yes. If adsorption is the rate determining step and it's exothermic, then increasing temperature decreases the equilibrium coverage and slows the overall rate. If the rate equals K desorption times the coverage of a dash S, and the coverage equals K adds times A times E to the negative delta H adds over RT. If delta H adsorption is negative and large enough in magnitude, it can overwhelm the positive activation energy for desorption. The apparent activation energy equals E desorption minus delta H adsorption. This can be negative. Let me summarize the key lessons from this lecture. Lesson 1. Rate laws are quantitative tests of proposed mechanisms. A single inconsistency kills your mechanism. Lesson 2. Fractional reaction orders almost always indicate equilibrium steps, particularly adsorption equilibria in catalysis. Lesson 3. Not all atoms are equal. Active sites are special locations with unique geometric or electronic properties. Lesson 4. Competitive adsorption for active sites controls not just activity but also selectivity in catalysis. Lesson 5. The best catalysts bind reactants neither too weakly nor too strongly. This is the Sabatier principle. The story of surface catalysis is a beautiful example of how careful experiments and mechanism-based reasoning lead to profound insights. Those strange fractional orders and product inhibition terms that initially seemed like experimental errors were actually crucial clues to the underlying molecular mechanism. Understanding mechanisms at the molecular level enables rational catalyst design rather than empirical trial and error. And this framework of using rate laws to probe mechanisms extends far beyond heterogeneous catalysis to enzyme kinetics, atmospheric chemistry, and materials synthesis. Always remember, the rate law is your experimental window into the hidden world of reaction mechanisms. Measure it carefully, interpret it rigorously, and it will reveal nature's secrets.